Welcome back. So today we're going to talk about another application for GPUs, which is sparse matrix vector multiplication. So another name for this is SpMV, right? So that's the abbreviation for this problem. Now, before I start, you might be wondering why I'm talking about sparse matrix vector multiplication, because I've actually mentioned several times previously that GPUs are not optimized for sparse matrix operations, right? I mentioned that they're excellent for dense matrix operations, but there are a number of properties of sparse matrix operations that make them not suitable for GPUs. Okay. However, today we're still going to focus on this problem, and the reason is that, well, first of all, GPUs are so powerful compared to CPUs. Okay, like a good GPU could be like 10 times faster than a high-end CPU. Okay, so it has so much computing power that even though SpMV is not the ideal application for GPUs, if you run SpMV on GPUs, you can still get higher performance on the GPU than the CPU. Okay, just because the GPU is so much more powerful. Okay, and the other reason that we're going to study SpMV is that it's actually a very fundamental problem, which if we can do SpMV efficiently, we can actually use this as a primitive for solving many other problems. Okay, these include things in optimization. They include solving linear systems. They include like eigenvalue methods, which have other applications in themselves. They include things like simulations, which often for things like finite elements, and then also for data analysis. Okay, so many applications are actually built on top of this SpMV operation, right? If you take these applications and you look inside them, what you see at the end is some sort of SpMV operation. Okay, so SpMV is actually really crucial to many things, and so therefore we want to study them. And so even though this problem is not the best problem for GPUs, we're still going to look at methods to try to implement this as efficiently as possible on GPUs. Okay, so just to state the problem more concretely, so sparse matrix vector multiplication, so we have a sparse matrix, and we simply want to multiply it by a dense vector. Okay, so the example is over here, right? So we have a sparse matrix, and what that means is that many of the entries in this matrix are zeros. Okay, so only these black parts, right? Only these are the non-zero values, right? And here, the matrix is about half zeros, but in practice, if you we're going to be working with very large matrices, right? Dimensions are going to be like, a million by a million, or maybe 100 million by 100 million. Okay, so those are huge matrices, and only a very small part of those will be non-zero. Okay, so you could have a million by million matrix, but each row has on average, let's say 10 non-zero values. Okay, so it's that's like sort of 1/100,000th of the matrix is actually non-zero. Okay, so it's very, very sparse. Okay, we're going to take the sparse matrix and you're going to multiply it by a dense vector. Okay, so we're not assuming that many entries in this vector are going to be zero. In fact, we basically assume that all of these entries are non-zero. Okay, and that's going to produce another dense vector. And that's it. That's the SpMV operation. Okay, but it's actually very, very useful. Okay, now before I talk about how to actually implement this, let's see why we're concerned about sparse matrices. Okay, and the reason is that many matrices that we deal with in practice are sparse. Okay, so the definition again is we have an m by m matrix, but there's just a very small fraction of non-zero elements. And so where do we see sparse matrices? Well, one example is if you work with finite elements to do some sort of simulation, right? For example, if we can use a matrix as a way of representing this this car here, this sort of wire mesh for a car. Okay, so the way you do that is you see that this wire mesh here is composed of a bunch of vertices and then edges between some of those vertices, right? So let's say there are 100,000 vertices in this picture. Okay, so then what we're going to do is we're going to make a matrix that's 100,000 by 100,000. Okay, so each row or column of that matrix corresponds to one of these vertices. Okay, and then now whenever there's an edge between two vertices, right, we're going to put a non-zero value in that corresponding row and column. Okay, so for example, if vertex 5 is connected to 7, okay, then in, let's say, row 5, column 7, we're going to put a non-zero. Okay, now this is going to lead to a very sparse matrix. And the reason is that you see each of these vertices is only connected to like, very few other vertices, like maybe 4 other vertices. Okay, so that means that in each row, right, each row corresponds to a vertex, right? And the non-zeros in that row correspond to connections to other vertices, edges to other vertices. Okay, now each vertex only has 4 edges to other vertices, let's say. So that means that even though it's 100 by 100,000, 100,000 by 100,000 matrix, there's only going to be 4 non-zeros per row. Okay, so it's a very sparse matrix. Okay, so that's one example. Another example is we can use these sparse matrices to represent something like the internet. Okay, and the connectivity between different, let's say, websites on the internet. Okay, so here, what we're going to do is make a matrix where each row, so suppose you have some number of websites on the internet. Okay, let's call that n websites. Then we're going to make an m by m matrix. And that matrix, again, represents the connectivity on the internet. So if there's a connection, if there's like a hyperlink between web page I to web page J, right, then we're going to put a non-zero value in row I, column J of this matrix. Okay, so therefore in each row, the only non-zeros are the connections from that website, for the row, to other websites. Right, so each website is only going to connect to like maybe a few dozen or, at most a few thousand other websites, right? Maybe 100,000 other websites, but it's not going to connect to every other website on the web, right? On the other hand, you have billions and billions of web pages. Okay, so your matrix, the dimensions is going to be like billions by billions, but each row is only going to have maybe a few tens or maybe a few thousand non-zero values. So again, that's going to be a very sparse matrix. Okay, and there are many, many other examples where sparse matrices come up. Okay, so now, and using these representations, it turns out that you can compute many interesting things simply by by multiplying these matrices by a vector. Okay, so for example, there's this famous PageRank algorithm by Google, right? And this is basically taking the web connectivity matrix and then multiplying it by this vector. And if you do that multiple times, then you basically end up computing something like an eigenvalue, an eigenvector of this matrix, and that tells you something about the popularity of the different websites. Okay, and that's simply based on SpMV. And this is why we want to do SpMV. Okay, so now let's look at why it's hard to do SpMV, okay, especially on GPUs. So, so now the operation, so just to be concrete, what we're trying to do is we're given a sparse matrix A, right, and then X is a vector, and then you want to compute A times X. So what that means is if the output is B, right, then the ith entry of B is just, you take the ith row of A, right, and then you multiply that, or you do the dot product with the vector. Oh, I'm sorry, this should be an X over here. Sorry about that. Okay, and now this computation is actually memory bound. Okay, what that means is that if you look at how many memory operations this SpMV does versus how much computation. Okay, so you see that each time we, for each index of B of I, right? So we're adding together basically n of these products over here, right? So each time we need to get 2 values, one from A, one from X, right? And so those are memory operations, right? And then you multiply them, so that's an arithmetic operation, and then you add that to your running sum. Okay, so that's also arithmetic. Okay, so therefore we're doing 2 computes, right, the multiply and the add, for every 2 memory operations. Okay, so that means that this computation is very much memory bound, because usually we want to do many computations for each memory operation. And here you're doing just you're doing basically one one computation per memory operation. Okay, so to give an example of how much this can impact performance, suppose you have a GPU, right? Something like this card over here, this GTX card, and it can basically do 1.5 teraflops, so 1.5 trillion computations per second, and it has about 200 gigabytes of main memory bandwidth. Okay, now if suppose that so 200 gigabytes basically means that you can read 50 billion floating point values, right? And so for each floating point value you read, because you're going to do one computation for that, you're going to end up doing 50 gigaflops of computations, okay, compared to 1.5 teraflops potentially, right? So you're actually getting only 1/30th of your potential computational power. Okay, so this is one problem that, this is one reason SpMV is hard, okay, because it's a very memory-bound operation. Another reason it's hard to do is that the matrices we work with may either be regular or they could be irregular. Okay, so sometimes they're regular. So I talked about this finite elements operation. This representation. Right, so in that case, you could have, we're basically using a matrix to represent something like a grid, right? And you could end up with something which is fairly regular. So for example, most of the non-zero values may be along the diagonal of the matrix. Okay, so you have a few other diagonals which are also non-zero, but it's mostly the non-zero values are on these diagonals. Okay, so that's a regular type of matrix, and it makes it easier to deal with, because, for example, each row has about the same number of non-zeros. Okay. On the other hand, if you work with something like a web matrix, right, those could be highly irregular, because there could be no pattern to where the non-zero values are, right? Because there's not necessarily much of a pattern to the connectivity of different websites. I mean, there is some sort of pattern, right? I mean, they're kind of arranged in a hierarchical fashion, but more or less, you can think of them as kind of like random connections. Okay, so if they're random connections, then this causes problems because, well, for example, when you go access these matrix elements or the corresponding vector elements, right, you might have to go to random memory locations. Now, remember, in one of our GPU lectures, we said that to get good performance on the GPU, it's really important to get coalesced memory accesses. Right, so that means that if you access a data item, right, you actually want to access all of the surrounding data items. Right, you don't want to just access a bunch of random data items, because for each data item you access, you need to get the entire memory segment surrounding that element. Okay, so that's like 32 other elements, and if you only want one of those elements, then you're wasting like a large part of your bandwidth. Also, if these different rows have different numbers of non-zeros, then depending on how you assign threads to the non-zeros to do the work, you could have a lot of load imbalance. Okay, so for example, if you assign one thread per row to do the work, right, then you can get big load imbalance, because some of the rows can have a lot of non-zeros, so that thread has a lot of work to do, and some of them have very few non-zeros. Okay, so those are some of the problems with doing SpMV, especially on GPUs. Okay, so now we're going to talk about a number of different techniques that people have come up with to do SpMV on GPUs, and they're basically based on different ways of storing the sparse matrix. Okay, so the sparse matrix, there are a bunch of zero values in there, so of course you don't want to store all of those zeros. Okay, in fact, you can't store all of those zeros, because the matrix would be too large otherwise. Okay, so there are many ways that we can avoid storing these zeros, right? And depending on which way you choose, you get different types of performance properties. Okay, so and we're going to be looking at a number of these different ways. Now, all of these methods, right, they're always going to be storing the matrix and the vector in global memory, right? Because these matrices and vectors, even though they're sparse, even though the matrix is sparse, it's still very large. Okay, it's like hundreds of megabytes or gigabytes in size. So it can only be put into the global memory. Okay. Yeah. Now, in terms of this computation to memory access bound, right? There's not much we can do about that because you know that's the nature of matrix vector multiplication, is that you have to read you know, 2 values and then you only do 2 math operations on them. Okay, this is kind of unlike a matrix multiplication, where if you read a few values, you can actually do many computations on those, right? So here, you know, we're stuck, okay, because of the application that we're working with. Now, some of the other issues, though, we can try to deal with. Okay, so one of them is the irregularity of the matrix axes, right? So the matrix is sparse, and the non-zeros can be in random places, right? But because we're only storing the non-zero elements, okay, then depending on, we're going to talk about a number of different storage formats, and some of them can actually lead to very good memory coalescing when you access the matrix, okay? And some of these storage formats can also help us improve load balancing when you compute on the matrix, okay? And then also we can assign threads in a way to sort of minimize the divergence between the threads. So we can try to ensure that the threads will be doing the same operations. Okay, so we can, to some extent, by using these different storage formats, we can improve, we can get pretty regular accesses to the matrix elements. Okay, however, in addition to the matrix elements, you also have to access the vector elements, right? Because, for example, if we go back to this equation over here, right, you see that not only are you going to access the matrix elements, you're also going to be accessing the vector elements. Okay. In fact, you do one each for every one of these products that you have. And for the vector axes, so there are different ways of regularizing the vector axes. Okay, of making them less random and less jumpy. Okay, so one of them is to take a matrix and then you can somehow permute the rows and the columns. Okay, so that the matrix becomes more regular, has more structure. So this is shown in this picture over here, where you have one matrix on the left, right? So this looks like pretty much a random matrix, right? Well, I mean, there are patterns, but the distribution of the non-zeros is quite you know, chaotic. And then it turns out that you can actually do some operations on this, and you can permute some of the rows and columns. And after you do that, you're going to end up with a matrix on the right, you know, which looks a lot more regular. Okay, I mean, there's still some irregularity to the matrix on the right, but it looks a lot better than the one on the left. And when you and if you're working with a matrix on the right, then that helps you regularize your vector axes. Okay, so instead of like jumping to a bunch of pretty much random vector locations, you can have much more regular axes to the vector. Okay, now finding this permutation, right? Finding this way to transform from the left matrix to the right matrix. Okay, so they're actually the same matrix, right? So they capture the same data, except for you relabel the different rows and columns. Okay, however, you have to somehow find this relabeling, right? And this is usually an expensive process. There are many different algorithms for doing this, but they're all pretty expensive. However, the thing is that you don't have to do this over and over. You can just do this once per matrix. Okay, so once you know how to go from the left to the right, then you're just going to transform the matrix, and you're always going to work with the matrix on the right. Okay, so you pay that cost once, and it could be worth it. Okay, now today we're not going to talk about how to regularize the vector axes. Okay, so that's that can be like a lecture or even multiple lectures in itself. Okay, we're only going to be addressing the irregularity of the matrix axes. Okay, so we're going to be looking at these different matrix storage formats and how they can improve things like coalescing and load balancing. Okay, so the first format we're going to look at is called the DIA format, or diagonal format. Okay. Now, I should say that the differences between these different formats is that different formats are suited to different types of matrices. Okay, they're optimized to different types of matrices. So, for example, this diagonal format. Okay, this is optimized to matrices that basically consist of a small number of diagonals. Okay, the non-zeros are mostly on the diagonals. Okay, so for example, if we go back to this this matrix on the right, okay, you see that most of the non-zeros are on the diagonals. Okay, I mean, you do have some non-zeros on these non-diagonal parts, like over here and over here, right, which can cause problems. But by and large, the non-zeros are on the diagonal over here. Okay, so there's a few diagonals along which all of the within which all of the non-zeros lie. Okay, and this also shows you why the right representation of the matrix is so much better than the one on the left. Okay, because the one on the left, you see that basically every diagonal, right? Oops, why is this not working? Right, you see that you know, you can, okay, you can draw any diagonal, and it's got and that diagonal would have some non-zeros on it. So if you try to use the diagonal format to represent the matrix on the left, right, it won't save you anything because you need to keep basically all the diagonals. Okay, if you use it for the thing on the right, right, then you can throw away all of these diagonals because you know, none of these diagonals have anything, so you can throw all of them away. Okay, you just have to keep the ones which are towards the main diagonal, and then you do have to keep the ones which are sort of like over here. Okay, but you could actually do something different for these things and these things. Okay, so I'm not going to get into that. Okay, so anyways, how does this diagonal format work? All right, so here's the example of a matrix, right? So we're going to just try to capture the data on the diagonals. Okay, so now which diagonals in this matrix are non-zero? So you have this diagonal over here, but that's only got zeros in it, so we're going to throw that away. Okay, you have a diagonal over here, right? So this has got non-zeros in it, so we're going to keep it in this diagonal format. Okay, this diagonal has only zeros, so you throw it away. This has non-zeros, so you keep it. This has non-zeros, you keep it. And then these two have only zeros, so you throw them away. Okay, so altogether, you just, the only diagonals we keep are the ones with the non-zeros, right? So we keep 3 of them. Okay, and then we're just going to store the data that's in these diagonals. Okay, so in particular, we're going to convert this matrix, right, into this data matrix over here. And the way this works is that this data matrix, each column is going to capture the non-zeros in one of A's diagonals. Okay, so for example, this diagonal over here corresponds to this first column, right? The second column corresponds to the this diagonal on A. Okay, now we need to know, so now we know which diagonals we're going to keep, right? But how do we know where the non-zero values in that diagonal are? Okay, and the way you know that is that we're going to extend each of these diagonals, in this fashion. Okay, so they sort of meet up at this line which comes at the top of A. Okay, so that means that there would be an element over here and an element over here, right? If we extend this diagonal that contains 5 and 6 to the top of the matrix, right, there will be 2 additional elements, but you know, but we have zeros at those locations, okay, or those values actually do not exist in the matrix. So therefore, we're going to represent them with these stars over here. Okay. Now for the main diagonal, the one with 1, 2, 3, 4, right? This you know, all the elements are occupied. Okay. And then for the next diagonal, the 7, 8, 9, 1, right? If you extend the diagonal, then you're going to end up with a 0 element over here, and that's going to be represented by the star over here. Okay, so this captures all of the elements on each of these diagonals. Okay, so next, you have to know which diagonals we actually captured. Okay, because yeah, you know, in this matrix there are 5 potential diagonals, or sorry, actually 6 of them. No, how many of them are there? There are, let's see, 1, 2, 3, 4, 5, 6, 7 of them. Oh, okay, sorry. So there are 7 potential diagonals, right? And we only stored 3 of them. So how do we know which ones we stored? So this is going to be stored in this offsets array. Okay, so this offsets basically tells you which diagonals you stored. And the way to read this is that the 0 here represents the main diagonal. Okay, so that's like the longest diagonal in the matrix. That's the 1, 2, 3, 4 diagonal. Okay, so this means that so the 0 here indicates that we did store the main diagonal. Okay, the -2 means that you actually stored a diagonal that's like 2 left of the main diagonal. Okay, so that's the 5, 6 diagonal. Okay, and the 1 over here means that you also stored a diagonal which is 1 to the right of the main diagonal. Okay, so therefore this diagonal format consists of 2 parts. It's got the data matrix, which stores the elements, the values on the diagonals, and then if some of those elements don't exist, then you use a star at those locations. And it's also got this offsets array, which tells you which diagonals you stored. And these offsets are represented with respect to the main diagonal, which is labeled as 0. Okay, so that is the diagonal format, and this format is optimized only for certain types of matrices, only for the ones where there are only a few non-zero diagonals. Okay, so you can see why, because let me sort of clear this up a little bit. Okay, so then so here we had 3 non-diagonals. Three non-zero diagonals. Okay, now if you had a matrix with basically all of the diagonals were non-zeros. Okay, then how big would your data matrix be? Then your data matrix would be the same size as the original matrix. Okay, so then you don't save anything in that case. However, if all of your elements lie on just a few diagonals, right? Let's say they lie on, let's say, 3 diagonals, okay? And then your data matrix would only have 3 columns and then n rows, okay? Instead of n columns, n rows. So then you save a lot. Okay. Now, it turns out that there are matrices that we care about in practice that are that have this diagonal property. Okay, so we can so these matrices come from things like stencils or grids, right? Or these finite element things. Okay, so this diagonal format has its uses, but it is specialized. Okay, so the next format is we're going to talk about the ELL format. Okay, so this format is basically specialized for matrices where each row has about the same number of non-zeros. Okay, not necessarily exactly the same number of non-zeros, but approximately. Okay, so for example, if you look at this A matrix here, then the first row has 2 non-zeros, right? And then the next row has 2 non-zeros, and then 3, and then 2. Okay, so they have about the same number of non-zeros. So in that case, the ELL format can be efficient. So the way that the ELL format works is that you start with this sparse matrix A, and then you're going to represent it using 2 smaller matrices, the data matrix and the index matrix. Okay, and the way this works is that assume that we know that A, each row has, so A is going to be an n by m matrix. Okay, so this is n by n, right? But assume that we know that each row has at most m non-zeros. Okay, so I'm going to write non-zero as nz per row. Okay, oops, per row. All right, and then the data matrix is going to be an n by m matrix. Okay, so now each row of the data matrix is just going to store the non-zeros from that row of the A matrix. Okay, and since we know that each row has at most n non-zeros, right, then we only need to make m columns for data. Okay, and the indices is also going to be an n by m matrix. Okay, so here, if m is a lot smaller than n, right, then we save a lot of space by using the data in the indices matrix instead of A. Okay, so the way that the data matrix works is that it just stores exactly the the non-zeros of A, okay, in each row of A. And it stores them by in a left justified manner, okay, meaning that you push these non-zeros as much to the left as possible. Okay, so for example, in the first row, you have 2 non-zeros, right? So therefore, we're going to store them in the first 2 columns of data. Okay, yeah, so we're going to store 1, 7 in the first row of data, right? And then you're going to store 2, 8, and then so on, right? 5, 3, 9 in the third row, and so on. Okay, and you store them as much to the left as possible. And after that, so now we've stored the values from A, but you need to know which columns they come from, right? And so that's what the indices matrix tells you. Okay, the indices matrix tells you for each of the values that you stored in the data matrix, right? Well, we know which row it comes from because if we're working with the ith row in the data matrix, then it came from the ith row in the A matrix. Okay, so the row we already know. Okay, however, what about the column? Okay, so for example, for this 8 value here, right? So this is lying in the so the columns are going to be, so we have 0, 1, 2, 3 here, right? So we need to remember that 8 actually came from column 2. Okay, and the way you do that is that you just write column 2. Okay. Yeah, and then for example, for this 9 over here, right? This came from column 3, so you just put a 3 in that location. Okay. Now, because A, right? So so M here is the maximum number of non-zeros per row of A. Okay, but you could have rows which have less than M non-zeros, and if that happens, then we're just going to store these stars, okay, to represent that we actually do not have M non-zeros in that row. Okay, and then likewise in indices, you also store a star. Okay, so the yeah, so this is effective for matrices where you have more or less the same number of non-zeros per row, and if that's the case, right, then you're not going to have too many of these stars, right? So the stars are like wasted space, right? If you only have one row which has a huge number of non-zeros, okay, but all the other rows have, let's say, 1 non-zero, okay, and let's say one row has 1,000 non-zeros. Okay, then you're going to have to make 1,000 columns. But for each of those columns, right, for all the rows which only have 1 non-zero, you're going to have 999 of these stars, right? So that's all being wasted. Okay, so you want basically all of the rows to have the same number of non-zeros so that you don't have these wasted star things. Okay, so next we have the COO format. So this stands for coordinate. Okay, COO. And this is basically like it's a very general format, and it just simply it's going to iterate through A in a row-wise in a row major ordering. Okay, and then it's just going to store all of the non-zeros that you encounter in this ordering. Okay, so for example, the first non-zero you encounter is going to be 1, right? So we're just going to store the 1. So the COO format is going to have three arrays to represent A. Okay, so the data array is just going to store all of the non-zero values. Okay, so you see that all of these values, 1, 7, 2, 8, and so on, these are exactly the non-zero values in the A matrix. Okay, in the order that we look at this matrix in the row major order. Okay, now for each of these non-zeros that we store, right, for example, for 1, we just store which row and column it's in. Okay, so for example, the 1 is in row 0, right, and it's in column 0. So you just store these in the row and the indices arrays. Okay, so likewise, 8 over here, right, this is like the fourth non-zero element, and this is in the first row. So we store 1 here, and it's in column 2, so you store 2 here. Okay, so this is why it's called this the coordinate format, because for each non-zero, right, you just store the coordinate of that non-zero in A. Okay, so so this is a completely general purpose format, right, because it doesn't care where the non-zeros are, right? For the diagonal format, we wanted the non-zeros to be on the diagonals. For the ELL format, you wanted the rows to be the same length. But for the COO format, you completely don't care where the non-zeros are. Okay, now there's a bit of inefficiency to this COO format because you see that for the values that lie in the same row, right? So for example, for 5, 3, 9, right? They all lie in row 2. So then in that case, we actually wrote down the value 2 3 times, right? We repeated the same value multiple times. Okay, and this happens whenever you have multiple values in the same row. You're going to have to repeat that row multiple times in the row array. Okay, so this, so that's going to cause you to use more storage. And when you read these arrays to do the computation, you have to also use more memory traffic. So is there a way that we can avoid this duplication in the row array? So it turns out that there's another format called CSR. So this stands for compressed sparse row. So this is very similar to the COO format, except for there's no repeats in the row array anymore. Okay, in fact, it doesn't have a row array. So the CSR format has an indices and data array just like the COO format. Okay, and they represent the same thing. So for example, the data array just represents the non-zeros in A. Okay, the non-zero values. Okay, and the indices represent the columns where these non-zeros occur. So for example, the 8, right, that's going to occur in column 2, right? The 9, right, which is over here, it occurs in column 3. Okay, so you put a 3 over here. Okay, so the usage of the data and the indices in CSR is the same as COO. The only difference is that the CSR format, instead of using a row array, it's going to use this thing called pointer. Okay, this pointer array, what it does is it tells you where the different rows start. Okay, so so in general, if you have so let me just show all this stuff over here, right? So if you have an m by m matrix, okay, so then this and then let's say that in total you're going to have let's say m non-zeros, okay, total. Okay, then the indices and the data array are both going to have size m. Okay, but the pointer thing is going to have size n plus 1. Okay, so you're going to have an index in the pointer array for each row of A. And the values in the pointer array indicate where the different rows start in data in indices. Okay, so what I mean by that is where does the data for the first row start? Okay, so the first row of A has 1 and 7. Okay, now where's the data being stored in the indices and data array? Well, the storage, so it's being stored over here, right? And the storage starts at index, so let me actually write these indices, okay? So 0, 1, 2, 3, 4, 5, 6, 7, 8. So the storage actually for row 0 actually starts at index 0 over here. Okay, so that's what this 0 represents. Okay, now the 2, right, this represents where the storage for, so this is going to be rows. Okay, 0, 1, 2, 3, 4. Okay, so this is a row. Okay, now for row 1, the storage for that is going to start at index 2 over here. Right, you see that for row 1, right, we're going to store the data 2 and 8, right, so that's being stored over here. And this starts at index 2 over here. Okay, and that's what this 2 means. Okay, it means that if you want to look at the data for row 1, right, go to index 2 in both the data and indices arrays. Okay, now what about something like, let's say row 4. Okay, so suppose you want to get the data for, or sorry, not row 4, row 3. Okay, so row 3 is this one. Right, so we want to get the data that's over here, right? Now, how do we find where the data for row 3 starts? Okay, well, you go to index 3 in pointer, and this sets the value 7, so that means that all of this data starts at index 7 over here. Okay, so that's how you interpret all of the values in the pointer array, right? The pointer array, the reason it's called pointer is that these are basically pointers that tell you where to go look in the indices and data array to get the values for the different rows, okay, for rows 0, 1, 2, 3. Okay. All right. Now, what about this final value for the pointer array? Okay. So this is basically telling you the size of the indices and data array. Okay. And the size is equal to the number of non-zeros in matrix A, right? Because you store one element in data for each non-zero of A. Okay, so you see that A has 9 non-zeros, right? And this is why the final value in pointer, right? That's not a pointer anymore. That's telling you that there are 9 non-zeros in data and indices. Okay, so now, so in terms of some code, the way that we're going to look at these is that suppose you want to get the data for the ith row. Okay, well then these indices are going to occur between pointer I and pointer I plus 1 minus 1. Okay, so for example, if you want to get the data for row 2, right? So let's clear this up a bit, right? If you want to get the data for row 2, right, which is being stored, where is this? 539, okay? Right, so this is occurring between indices 4 and 6, right? And the way you know that is you go to pointer of 2, right? And then you also going to go to pointer of 3, and then you subtract 1, right? And so that tells you that the data is being stored between indices 4 and then 6. Okay, so you have, so this is how you get this data, okay? And now for the elements in the ith row, right, that are between these two, that are between this index and that index, okay? So the way you tell which column each of those elements is in is that you go to indices, right? And then if you're looking for the jth element in the ith row, okay, then you go look in indices at location pointer I plus j. Okay, so for example, if you're looking at element 1 in the what are we talking about in row 2, okay? Let's erase this. So we're looking at element 1 in row 2, right? So that's actually element 1, since you start counting at 0, element 1 is actually this guy over here, okay? So that means that you go to pointer of 2, which is 4, right? And you add 1, so that's 5. Okay, so that means that we should go look in index 5 in both the data array and the indices array. So the data array tells us, so this 2 says that, okay, all right, the element 1 in the second row is in column 2. Okay, so the columns are, we have 0, 1, 2, 3, right? So this 3 is actually in column 2. Okay, and what is the value at that location, right? What value is actually in column 2 of row 2? Well, then you go look in the data array and you see that, okay, it's going to be a 3 there. Okay, so the way you can tell that is you go to data and then you go to index pointer I plus j. Okay, so might be a little confusing the first time that you see this, but just remember, so another way that you can kind of think of this is that you can think of it this way. Okay, so remember, so this is going to point at over here, right? This 2 is going to point over here, right? So the rows are, I'm going to mark where the data for the different rows are, right? So then you can think of these pointers as being pointing to the start of each row. Okay. All right, so that is the CSR format. And the final format we're going to look at, so this is a very widely used format. Okay, it's very flexible because you can have non-zeros in any location, right? So unlike DIA or ELL, you can have any kind of structure for your non-zeros. It's also quite efficient because unlike the COO format, right, we don't have any waste in the pointer and in the pointer array. Okay, unlike the row array for COO. And then, yeah, and it's a very popular format, which is used quite often, okay? And then, so there's a very similar format called CSC, okay? So CSR just means that the way you iterate through the rows is in row major format. So that's why it's called compressed sparse row, right? So the CSC is just compressed sparse column, okay? So that just means that you iterate through the non-zeros in a column major format, okay? It's very similar. Otherwise, it's just completely the same thing as CSR. Okay, so the final format we're going to look at is called the hybrid format. And this is going to be a combination of several previous formats. Okay, so in particular, it's going to be a combination of the ELL format and the COO format. Okay, so now, so when you would use this hybrid format is that if you have a matrix where most of the rows have the same length, let's say L, okay, have the same number of non-zeros. Okay, however, you have a few rows with, let's say, a lot of non-zeros. Then, if you use the ELL format, right, you're going to have to make the size of the matrix, the number of columns, be equal to the maximum number of non-zeros in any row. Okay, so that could be like much larger than the average number of non-zeros. So then it's very wasteful to use the ELL format. However, so the way we're going to, so this hybrid format is going to combine ELL and COO. And the way it works is that you're going to take all of the, you're going to take this L, which is basically like the average length of the rows. Okay, and then you're going to take, for each row, you're going to take L elements. Okay, and represent them using using ELL. Okay, so ELL, requires that all of the rows have about the same number of elements, and that's fine for our case because we're just going to take L elements from each row and then put them into the ELL format. Okay, however, that's going to leave some elements that we didn't, that it's not going to cover some elements. Okay, so for example, in this matrix, right, if you take two elements per row and then put them into the ELL format, that's going to leave these green elements that you haven't covered yet. Okay, and then the way that you cover these few remaining elements is that you're going to use the COO format to store them. Okay, so you use the ELL format to store this blue matrix over here, right, with all the blue values. Okay, but you ignore the green values. Right, and then for the leftover green values, right, now imagine that the blue values are not there anymore. So you have a matrix with just 4 green values. Okay, so then you can use the COO format to store these green values. And the idea is that since most of the rows, right, so the hybrid format is suitable when most rows have about the same length. Okay, so that means that most of this matrix you're going to be storing in the ELL format. Right. However, there's going to be a small fraction that you store in the COO format. Okay, so that's the hybrid format. Okay, and this can actually represent so you can use this to represent any matrix, right? Because in the worst case, you just represent everything using COO. Okay, but it's going to be very efficient when most rows have about the same length, so that the ELL part is going to be large and the COO part is going to be small. All right, so this is showing which kind of format you should use depending on the structure of your matrix. Okay, so so if you have a, and the way we're going to look at these is that you can go from very unstructured matrices to structured matrices. Okay, so by from structured to unstructured. Okay, so by structured we mean something like these diagonal matrices. Okay, so they have a lot of structure to them. Okay, so in that case, you can use something like the diagonal format. Okay, for the ELL format, right, you don't care where the non-zeros are, but you try to ensure that you have the same number of non-zeros per row. So there's some sort of structure there for the ELL format. It's less than what you assume for the diagonal format, but you still make some assumptions. Okay, and then for even more unstructured matrices, you can use the CSR or the hybrid or the COO format. Okay, so the right matrix format depends on the type of matrix that you work with. Okay, so before you decide on a format, you have to think about the applications that you're geared towards. Okay, if you're geared towards things like stencils and grids and other types of regular matrices, okay, then you should go with these regular formats. Okay, or you should have something in your code which says that if I'm dealing with something regular, okay, then I'll use one format. Okay, if I'm using dealing with irregular matrices, I'm going to use other formats. Okay, so now we've talked about how to store matrices in different formats. So now we're going to look at how to actually do the SpMV computation when you have the matrix in different formats. Okay, so I'm going to skip over the DIA format. So the first one I'll cover is the ELL format. Okay, so remember that the ELL format is that we're assuming each row has about the same number of non-zeros. So if you have a matrix A up here, right, we're going to form two matrices to represent this A, which is the data matrix and the index matrix. Okay, so the way that we're going to compute with the ELL format is we're going to assign one thread to process each row of data in indices. Okay, so suppose you have 4 threads. Then we're going to assign a thread 0 to process the first row of data in indices, right? So 0 is going to go here, right? And then 1, and then 2, 3. So that's going to be 4 threads, 1 for each row of data in indices. And what the threads are going to do is, so the threads are going to run multiple iterations, right? Because each thread needs to process the entire first row or second row or whichever. Okay, so it's going to do that in a for loop. So for the first iteration of the for loop, all the threads are going to process the first element in data. Okay, and indices also, right? So they're going to process this one also, all right? And then in the second iteration, they're going to process the second element. Okay, third iteration, third element, and so on. Okay, so all right, so so now first of all, since we're assuming all the rows have about the same number of non-zeros, okay, then we see that if we do processing in this way, we actually get good load balancing, because you know, so the number of non-zeros is basically the number of columns of data and indices. Okay, and so so we see that each thread, right, it's going to process, it's going to iterate through all the columns, and since all the columns have about the same number of non-zeros, then we actually get good load balancing between all the different threads. Okay, so next, now there's something which I didn't mention about data and indices, which is, so these are matrices, right? So, so how do you actually store these in memory, right? You have to take this 2D matrix and store it in a 1D memory, and usually we store matrices in row major format. Okay, however, for the ELL format, we're going to store the two matrices in column major format. Okay, so column major format just means that we're going to store them in this order. Okay, and same for indices. Okay, so for example, you see that the data matrix, right? The actual way it's being stored is in column major order, like that. Okay, now why do we store this in column major format? Okay, it's because this is actually going to help us with memory coalescing. Okay, because now consider the first iteration of all the threads. Okay, so we have 4 threads here. So let's assume that the threads belong to a warp. Okay, so a warp is going to be a consecutive chunk of, usually it's 32 threads, but in our case, let's say it's going to be 4 threads. Now, which data items is each thread going to access? Okay, in the first iteration, thread 0 is going to be accessing is going to be processing the 1 over here, right? Thread 1 is going to be processing the 2, right? This 2 over here, right? And then thread 3, and then thread 2, and then 3, right? So in the first iteration of the loop that these threads are doing, right? They're processing these elements from data, right? The 1, 2, 5, 6. And now, because you store data in column major format, then you can see that 1, 2, 5, 6 are consecutive in memory, right? So you have these 4 threads, and they're processing consecutive elements from memory, right? So the 4 threads are going to belong to a warp, and now this warp is going to make these memory accesses for 1, 2, 5, 6, and because it's consecutive, we're going to get a coalesced memory access, okay? So even though these 1, 2, 5, 6, they're like scattered in some random locations in the matrix, right? However, once you represent them using this this data matrix, and then you store data in a column major format, then when you access these matrix elements, you actually get a coalesced memory access. Okay, and the same thing for the indices, right? So in the first iteration, the threads are going to look at these indices, the 0, 1, 0, 1, and these are going to be coalesced like that because they're consecutive in the indices array. Okay. Now, what about the second iteration? The second iteration, the threads are going to be processing the second element from each row, which are these elements, right? And then you can see that these elements, where are they stored in data in indices? They're stored over here, okay? And again, these are consecutive. So therefore, we make coalesced memory accesses. Okay, so that's what's being represented in this picture down here. Okay, it's saying that in the first iteration of the 4 threads, right? These are the locations, the 1, 2, 5, 6 that we're accessing. Okay, and in the second iteration, we're going through the 7, 8, 3, 4, and so on. So what you see is that by using this column major format, all of our memory accesses are coalesced to the matrix. Okay. Now, finally, what is the actual code for doing this? Okay, so the actual code is, so each thread is going to figure out a row that it's going to process, right? And then it's going to go to that row, and then it's going to go to the, it's going to iterate through all of the columns in that row, right? And then first of all, it's going to go look in the indices matrix, or array rather, right? And then it wants to figure out what is in the rows row, right? So the rows row, right? And then the currently it's processing column n. Okay, so what index is in that location? Well, the way this is being stored is that so currently we have 4 rows per column, right? Yeah. So then this number of rows here, right? So this would be 4 because you have 4 rows in this matrix. Okay, so the thing that's actually being stored in the in column n and row is the way you can get to that in this indices array is by doing this computation over here. Okay, where this num rows is going to be 4. Okay, so that tells you which column of the matrix you're actually working with. Okay, and then you also need to get the value in matrix A at that location. Okay, so so to be sort of more concrete about this, so let's say that we are processing row 2, right? Or sorry, row 1. Okay, so row 1 over here, and then you're processing column 1. Okay. So then in that case, your n here would be 1, right? And then your row here would also be 1. So then we're going to look at indices in location. So this is going to be 4 here. So we're going to look at location number 5, right? So this is 0, 1, 2, 3, 4, 5. So we're going to look over here, right? And over here. So when you look in indices at location 5, what that is saying is that now this 8, okay, this is in row 1, and so we're looking at this, how do I say this? Okay, so when you go look in this location at indices, okay, the fact that this is a 2 is indicating that the value, whatever value is here, is actually in column 2 of the A matrix. Okay, right? So this is column 2 of the A matrix, right? So this is 0, 1, 2, 3. So this value is actually in column 2 of the A matrix. Okay, and what is that value? Well, then here we go look at data at location 5. Okay, we see that the value there is actually an 8. Okay, so the value is going to be 8, and the column is going to be 2, right? And then the final thing is that, well, in order to do this SpMV computation, right, sorry, so we're going to have to like multiply by this vector here, right? So this vector has 4 rows. And what you need to do is you need to take this row and multiply by this vector. So therefore, the 8 needs to get multiplied by, this is our x vector over here, by whatever this value is, right? So that's going to be x of 2. Okay, so we computed that x here is 2, right? The value is 8. So then here you need to do 8 times x of 2. Okay, and then you're going to add this into your dot product, right? The dot product of this entire row with x. All right, so that's how this works. Okay, so you so the iterations of the of this for loop are going to go through all of these columns, right? When you're in the nth column of the data matrix and the indices matrix, right? well, the way you get the value is through this computation, right? And then you're going to go look at the actual column that this refers to in A, right? And the value. And then now you need to go look into this column of X multiplied by the value. Okay, and then yeah, and then you keep adding this dot product into your overall Y value that you're producing as your output. Okay, so that's the ELL kernel. Okay, so next we're going to look at how to process the CSR format. So the CSR format, we're actually going to give two different ways of processing the CSR format. Okay, so the first one is going to be called the scalar kernel. So the way that this is going to work is that we're going to assign one thread per row of A. Okay, so so basically the rows of A are given in this pointer array over here. So that means that we're going to assign one thread per row, right? So remember that this final value here just represents the total number of non-zeros, so you don't have a thread there. And then once you do that, so what that means is, so the four threads are going to go look into this pointer array. So the first thread is going to see that its data starts at index 0. Right, that's what that's what the 0 in the pointer means. Okay, so the first thread is going to start over here. Okay, the next thread is going to see that its data is going to start at index 2. Okay, so then thread 1 is going to start over here. Thread 2 is going to start at 4, which is 3. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are the threads, right? So this is I. So then thread 2 is going to start over here, right? Yeah. And then thread 3 is going to start over here. Okay. So, and the threads are going to process A row by row. Okay. So thread 1 is going to be responsible for this row, or sorry, thread 0, 1, 2, 3. Okay. And they're just going to be processing the non-zeros in different iterations. Okay. The non-zeros in their row of A in different iterations. So therefore, in the first iteration, right, the four threads are going to process the first non-zero in their respective rows. Okay, so in the first iteration, thread 0 is going to process this element, right? Thread 1 is going to process this element, and so on. Okay, now in the next iteration, right, then thread 0 is going to process the next element in its row, which is located over here. Right, thread 1 is going to be processing this one, and then that one, and then that one. Okay, and then in the third iteration, right, or in iteration 2, the other threads 0, 1, and 3 are done with their rows, right, because they only have 2 non-zeros in their rows. But thread 3 needs to process, or rather, thread 2 needs to process this final element, right, the 9 in its row. Okay, so this is how it's working. Now, there's a problem with the CSR kernel, or scalar kernel, CSR scalar kernel, which is that it's not load balanced, okay? And the reason it's not load balanced is because you see that the amount of work that a thread does depends on how many non-zeros are in its row. Okay, so each thread gets assigned to one row, and the amount of work is just the number of non-zeros in that row. And different rows can actually have completely different numbers of non-zeros. Okay, so if you look at certain types of matrices, like web matrices, which are irregular, they can have a huge variance in the number of non-zeros per row. Okay, so you could have some rows that have, let's say, like one non-zero. Okay, or you could have other rows that have like 1,000,000 non-zeros. Okay, because if you have a web matrix, right, the number of non-zeros represents something like the number of websites that some website connects to. Okay, so you could have a few like sort of or actually you could have a bunch of sort of unpopular websites that only connect to one other website. Okay, so they only have one non-zero in their row. Whereas you could also have very, very popular websites that connect to thousands and thousands of other websites. Okay, so there's a huge variance in the number of non-zeros in different rows. And that's going to cause a very large load imbalance if you use the CSR scalar kernel. Okay, and also another problem that you can see is that the scalar kernel is rarely going to be coalesced. Okay, because for example, in this example, you see that in the first iteration, right, or rather iteration 0, right, you see that the memory locations that are being accessed by the different threads. So here you have 4 threads, and they're going to be in a warp. Okay, so ideally, you want the warp to make a coalesced memory access, meaning that you're accessing completely consecutive memory locations. Okay, but here this is not happening because they're accessing like these memory locations, which are not consecutive. Okay, now if it happens that so here you're not getting horrible non-coalescing. Okay, because these memory locations are still pretty close to each other, right? Because each the first row, it's only got 2 elements, right? So therefore the next thread, the memory location it accesses is just 2 indices away. So that's not too bad, right? At least it's not like 100 indices away. Okay, so if you have very short rows, then you can still have some degree of coalescing. Okay, however, if, for example, this first row, if it had 100 elements, okay, then the next thread, right, would be accessing something 100 indices away. And in that case, you would not have coalescing. The only way to have coalescing is if the memory addresses you're accessing are in the same memory segment, which only has 32 indices. Okay, so you can only be at most distance 32 away if you want to have any degree of coalescing. Okay, so here, the distances are not that large, right? So you could have a bit of coalescing, but in general, if the rows are somewhat bigger than 32, okay, then you're going to have very poor coalescing. Okay, well, that said, let's still try to figure out how this is how the CSR scalar kernel works. Okay, because next we're going to modify this kernel so that you actually get better performance. Okay, so let's first figure out the scalar kernel, and then we'll figure out how to modify this, how to improve this. Okay, so the way that this is going to work is that each row is going to first each thread is going to figure out a row based on its thread ID. Okay, so it's going to do this computation here, and then it's going to figure out where is the data for its row located. Right, so remember that the way you figure that out is to look inside the pointer array. Okay, so the data for row is located between pointer of row and pointer of row plus 1. So therefore, we're going to have this index that is going to iterate between the the start of this row and the end of this row. All right, and then we're going to look in data at this index. Right. So for example, if our let's do an example here. So if we're talking about row 2, right, then let's clear this up a little bit. Okay, then pointer of row 2 is going to be 4, right, and then this is going to be 7, and then so we're going to iterate between 4 to 6, right, and then we're going to look in data location 4 initially, right. So data location 4 is going to be this, right? So it's going to be the 5, right? Which is namely this element, right? And then and then we need to figure out which column 5 is actually in matrix A. Okay, so which column of A is this value 5 in? Okay, so the way you figure that out is you go look in indices at this 4 here, right? So then this is going to come out to 0, right? So this is saying that 5 is in column 0, okay? And so what that means is that if you have this X array over here, right, 0, 1, 2, 3, right, you're going to need to multiply this 5 by whatever is in the 0th index of X, okay? So that's what this thing over here is, okay? So you multiply these two values, you take the 5, and then you multiply this by X of 0, okay? And then you add that into your dot product, right? And then you add that into your Y value eventually. Okay, so this works, but it's not load balanced, and you don't get memory coalescing usually. Yeah, so it's usually got poor performance. Okay, so next we're gonna improve the CSR scalar kernel, and we're gonna have a CSR vector kernel. So the only difference here is that so for the CSR scalar kernel, you assign 1 thread per row, and here for the vector kernel, we're gonna assign 1 warp per row. Okay, if you assign 1 warp per row, then if you have many elements in your row, right, then each thread is going to have to process multiple elements. So so therefore thread I, right, the ith thread in the warp is going to process the ith element in its row plus the I plus 32th element, right? Because you have 32 threads in the warp. Okay, so each thread is going to get sort of 1/32 of this entire row. Okay, and the indices it's going to receive are it's going to be I first of all, and then I plus multiples of 32. Okay, so like 32, 64, and so on. Okay, so now if you look at what happens, okay, if you let's first look at the memory access pattern. Okay, so so here let's assume you have a bunch of warps like this. Okay, so we're going to assign the first warp to process row 0. Okay, so this is row 0 over here. This is all stuff for row 1, right? Row 2, and then row 3. Okay, so since you're assigning an entire warp to process this row, okay, then this is going to be basically how do I represent this? Okay, so here this is the first thread in warp 0. Okay, and this is the second thread in warp 0. And you see that these guys are accessing consecutive memory locations in indices and data, right? Like this guy is going to read these two things, and this guy is going to read these two things, right? And these data locations are consecutive. Okay. Likewise, you have warp 1, right? You have two threads. They're gonna be accessing these. So this guy is going to access. This is one thread, right? This is a different thread, and you see that the locations they access are again consecutive. Okay. So in general, you see that all of the threads are going to be accessing consecutive memory locations. Okay. So that means that we get much better memory coalescing. Okay, now you do have this problem that you know, if your row is either too short or if it's not a multiple of 32, then since you're assigning an entire warp of 32 threads to the row, okay, if for example your row is short, let's say it's only got like you know, 10 items in there, okay, then 22 of your threads won't do anything, right? So you're going to waste a lot of work if your rows are very short. Okay, and also if the row length is not divisible by 32, right? If, for example, you have a row that is like, you know, has 65 elements, okay, then most threads have 2 elements, right? But one thread is going to have 3 elements. Okay, so then in that case, you're going to have some threads which are imbalanced, somewhat imbalanced. Okay. However, so this means that you can still have some sort of imbalance. But within a, sorry, you can still have some sort of waste within a warp, okay? And furthermore, different warps can have different amounts of workload, okay? Because if you have a row with, let's say, you know, let's say 10 elements, and then you have another row with 1,000 elements, right? Then in the first row, you have a warp assigned to that, right? So each thread only gets like 1 element, or sometimes 0 elements in the first row, right? Whereas for the big row, right, then each thread is going to get like, you know, 1,000 divided by 32, so like 30 elements. Okay, so you're going to have a lot of load imbalance between the warps. Okay. However, it's better to have load imbalance between warps than to have load imbalance within a warp. Okay, right? So so intra-warp load imbalance. Okay, within a warp. Okay, this is more of a problem than load imbalance between warps. Okay, so let me try to explain this. Okay, so suppose you have a suppose you have 2 warps, right? So you have warp 1. Let's write W in a bit nicer way. So you have warp 1 and then warp 2. Okay, and suppose you have suppose both of these warps are like within the warp itself. Let's say, okay, they are severely imbalanced. Okay, so let's say that basically you have like 95% imbalance. Okay, so like basically that means that one thread is going to do like 20 times as much work as some other thread. Okay, and let's say that both threads are going to be are severely imbalanced like this. Okay, now remember that you have multiple threads executing on the same SM. Okay, so we have one SM here, and then let's say that both of these warps are executing on this SM. Okay, But because these warps have a lot of intra-warp load imbalance, right? Within the warp, they're imbalanced. Then no matter which warp you run on the SM, right? So what's going to happen is we keep switching between these two warps and running these on the SM until both warps are finished. Okay, but whichever warp happens to be running on the SM, because the warp itself is imbalanced, you're going to have a lot of imbalance. Okay, so overall, when you're running on this SM, you're wasting 95% of your time. Okay, because both warps that are running on this SM are imbalanced. Okay. All right. So this shows. So this is to show that intra-warp load imbalance is very bad. Okay. Now I want to show that inter-warp load imbalance is not so bad. Okay. So that means that if you have one warp which is much larger than a different warp, this is kind of bad, but it's not so bad. Okay. So the reason it's not so bad is suppose you have one warp, and let me write it this way, okay? So this is to sort of show the size of a warp. Suppose this guy is like, 100. So he's a big warp, okay? He's got a lot of work to do in that warp. And suppose this guy is like, 5. So he's a small warp, okay? He has a tiny bit of work to do in his warp. Now, when you execute these two warps on the SM, right, the two warps are going to share the SM, okay? So that means that when they run, you're going to have some schedule between the warps. Okay, so maybe the schedule is something like, you run warp 1 first on the SM, okay, and then you switch to warp 2, okay, and then maybe you run warp 1 again, and then maybe you run warp 1 again, right, just because you want to, and then you switch back to warp 2, and then maybe you do warp 2 a couple of times, right, or 3 times, and so on. So you keep switching between back and forth between warps 1 and 2. Okay, now eventually, since warp 2 only has 5 units of work, then after you schedule this warp 2 for 5 times, he's going to be done. Okay, so in the schedule, you're not going to see warp 2 appear again after 5 appearances. Okay. However, warp 1 is not done yet, right? Because it needs to do 100 units of work. Okay, so you can still schedule warp 1 on the SM. Okay, so this means that the SM always has work to do. Okay, because it's always executing at least one of the two warps. Right? Once warp 2 finishes, fine, okay? Then the SM is going to execute warp 1. Okay, but the SM is not idle at all, right? Because it's executing warp 1. Okay? Whereas for the case where if this guy had like 95% load imbalance, then whenever you execute this warp, right, then that means that out of the 32 threads in the warp, most of them have already finished, and there's just one thread that's actually working. Okay, so your SM has like 32 cores, right? So that means that if you have very high intra-warp imbalance, right, then only one of those cores is actually active. Okay, the other 31 cores are like not doing anything. So that's like a severe waste of the SM resource. Whereas for the inter-warp load imbalance, right, as long as I have at least one warp to run, right, which I always have at least one warp to run, right? Otherwise, if I finish all my warps, I'm going to be done with my thread block, and I'll go execute the next thread block, right? But anyways, I always have at least one warp to run, and so it's not so bad, okay? The only bad thing about only having one warp to run is that if you remember when we started talking about GPUs, right, we said that you actually want to have many threads active on an SM at the same time, right? You want to maximize your occupancy in order to do things like memory latency hiding. Right, so you wanted to switch between warps whenever one warp did a memory access, right? Then that warp becomes blocked, and so you want to switch to a different warp to do this latency hiding. Okay. Now, if you have imbalanced warps where this guy is basically finished after a while, and then eventually you're just left with a single warp W1, right? Then you can't do latency hiding anymore. Okay, so you do lose some performance because you've lost latency hiding. However, it's still better than having intra-warp load imbalance. Okay, so that's a very long explanation of why of the difference between intra and inter-warp load imbalance, but hopefully that convinces you why this CSR vector kernel, right, which only has inter-warp imbalance, is going to be much better than the scalar kernel, which has intra-warp imbalance. Okay. All right, so then let's so we didn't talk about the code for doing this. So the code is pretty simple. Previously each thread processed one row, right? So now you want each warp to process one row. So you first of all need to figure out which warp a thread belongs to. Okay, so that's just you take your thread ID and you divide by 32, and that's your warp ID. And whatever your warp ID is, that is a row that you're going to process. Okay, so just like before, you're going to get the start and the finish of that row, right? And then we're going to be keeping, so now you have a warp of 32 threads processing values from a row. Okay, so so basically for this row, you need to do like a dot product between a row and the between a row of A, right, and this X vector here. Okay, so now it's going to turn out that each thread in your warp is going to have part of this dot product. And in the end, you need to add together all these different parts to get the overall dot product. Okay, so each thread is going to be processing every 32nd element of this row. Okay, and it's going to be looking at these indices, which are the same for the CSR scalar kernel, except for now you just process every 32nd element of the row instead of every element of the row. Okay, and then in the end, you're gonna each thread is gonna have 1/32 of the entire dot product, right? So therefore, you need to add all those 32 values together. So that means that you're gonna do a reduction. Okay, so there's reduction is basically these values here, 16, 8, and so on. So if you remember, we had a reduction tree, right, which had a stride value, right? So that's sort of like the you pick another value that you're going to combine with. Okay, you pick another value stride distance away that you combine with. Okay, so this is going to be a reduction tree where basically it's like the values are going to be 16 away, right, and then 8 away, and then 4, and then so on. Okay, so if you do this, it's going to end up adding together all of the 32 values from the warp, right? And that is going to be the entire dot product between this sum row of A and the column and the vector X. Okay, yeah. Okay, so the final thing is going to be the COO kernel, and for this one we are going to so here we're going to assign one thread per non-zero. Okay, so all of these things are the non-zero values, and each one of them gets a thread. Okay, so the way to look at this is if you have 4 threads, right, then we're going to process this entire vector in multiple iterations. In the first iteration, right, the 4 threads are each going to get 1 value, right, and then in the next iteration they're going to get the next 4 values, and then so on. Okay, so so in this way you see that in each iteration all the threads get a value to process. Okay, except for maybe the final iteration where some threads don't get a value. Okay, but more or less you have perfect load balancing, right? Except for the final iteration. Okay, and also the memory accesses are completely coalesced, right? Because in the first iteration you access you access this chunk of data, right? So so thread 0 here is going to access these data items, and then thread 1, 2, 3, right? And all of these things are consecutive. Okay, and so you get perfect memory coalescing. Now the only sort of difficulty with doing this is that let's see. So one warp might actually span several short rows. Okay, because so as an example here, so suppose your warp has 4 threads. Okay, now then this actually covers 2 rows, right? So this the threads are going to cover this row, so this is 2 rows. Okay, and likewise when you start processing the next batch of 4 values, this is also going to occur in rows 2 and then also 3. Okay, now what you want to have happen is that you want these 2 threads, right? So they're both processing values from row 0. So therefore, each of them gets like part of the dot product from row 0. And you want them to add it together to get the entire dot product for row 0, right? So you want these guys to add their value together. Okay, like to add their value here. Okay, now but then for the next pair of threads, right? So we're first of all going to pair up the threads. Okay, the first pair is going to be distance 1 apart, and then distance 2, and then 4, and then 8, and so on. So just like we've been doing these reductions by doing these pairing things, right? We're going to do it again here, except for we have to make sure that when you pair with somebody, he's actually got a value from the same row as yourself. Okay, if he's got a value from the same row, then you should add it together to produce a dot product for that row. But if he's got a value from a different row, then you don't want to add with him, right? Because you don't want to add values from 2 different rows. So as an example, if you have these 2 threads, okay, so when they're being paired, they actually should not add together their values because this value is from row 0 and this is from row 1, right? Now these 2 things should get added because they're both from row 1, right? But for this pair of nodes, right, they don't add because they're from different rows, okay? These 2 things are going to add because they're from the same row, and these 2 things are going to add because they're from the same row. The 2, 3 don't add, and the 3, 3 they do add. Okay. So then after this happens, okay, so this is for the pairing for the for distance 1, right? For stride equals 1. Okay. So next we need to go for stride equals 2, right? And then 4, and then 8, and so on. Okay. So for stride equals 2, right? If this guy tries to pair with somebody who's distance 2 away, right? Then you see that, so for example, if we try this pairing here, okay? Now this these 2 guys should not add because they're from different rows. Okay, so let's just show the code over here. Okay, so what this is, what these things are saying is that, so here we're going for strides 1, 2, 4, 8, and so on. Okay, and what this is saying is that if you look at the row at this location versus the row that you pair with, versus the row of the location that you pair with. Okay, so we're pairing locations thread ID X and thread ID X minus 1. Right? If they belong to the same row, then we go ahead and add them. Okay, if they do not belong to the same row, you don't add them. Okay, and then next for distance 2, for stride 2, right, you compare thread ID X and this location, thread ID X minus 2. Okay, if they're from the same row, you add them. Okay, so then, for example, we try to pair these 2 guys, but we see that they're from different rows, right? That they're from rows 0 and 1, so you don't add them. Okay, so now you see that none of these things you actually add, except for when you get to this pairing. Okay, so here, right, these 2 guys, let's draw this again. Okay, they actually get paired, right? Because they're distance 2 apart. Okay, and they're from the same row, right? Because when you check this rows array, right, you see that, oh, okay, right, these 2 guys are from the same row. Okay, so then you add them. Okay, so when you add them, what do you get? Well, this guy on the left, right, when he did the first step over here, right, he got the sum of these 2 values, right? And now when you add this value and that value, right, so then that means that you're going to take, so here this is, this value here is equal to the sum of these 2 things, right? This value here is equal to this guy, right? So when you add them, you actually get the sum of all 3 of these things. Okay, right? So then this here, now you got the correct sum for all 3 of them, and the other guys, right? They've all got the correct sum for the 2 rows, for the row of 2 items that they belong to. Okay, so anyways, so you do this code. This is called a segmented reduction because you're actually you're doing reductions, but you're breaking these into a bunch of segments, right? So remember that we had a segmented prefix sum earlier, and that was also you do the prefix sum, but you break it into chunks, right? And so here now you can see why you can see an example where you need to break things into chunks, okay? Where the chunks represent different rows, and only the same row should be added together. Okay, yeah, and then so there's some restrictions to this code. So by the way, all this stuff I'm talking about, right? I didn't say this up to now, but this all comes from a very nice paper by these 2 guys, Bell and Garland. Okay, so they're NVIDIA guys, right? So they wrote this paper way back in 2009 at supercomputing. Okay, but it's still a useful paper. A lot of these formats that they introduced, right? So these guys sort of got the entire SpMV stuff on GPUs started. Okay, so they introduced all these like different kernels, and then they're still being used, right? The CSR kernels and so on, they're still being used. Okay, so nowadays people have improved on these, obviously, right? But the basic ideas are are still sort of adapted from the Bell and Garland paper. Okay, so this paper has more details if you want to look in more detail at this kernel or anything else about this stuff. Okay, so the final thing is now let's look at the performance of all this stuff. Okay, so we have a bunch of different storage formats. We said that they're suited to different types of matrices. Okay, so to test this hypothesis, we're going to look at two types of matrices, structured and unstructured. So structured, for the structured matrices, we're going to look at these so-called Laplacian k-point matrices. Okay, so they're basically diagonal matrices. Okay, so they're matrices where the only non-zeros are on certain diagonals. For example, the 3.1, you're going to have 3 non-zero diagonals. Okay, the 5.1, you have 5 non-zero diagonals, and the diagonals are very anyways, yeah. Okay, so then what you see is that because they're diagonal, right? Then here you're measuring. So you look at different types of these structured matrices. Okay, they're all diagonal ones. Okay, and you can see that you get the best performance using the diagonal format. Okay, in fact, you get improving performance as you increase the number of diagonals. You can utilize more and more of your GPU, so you're going to get somewhat better performance. Okay, so the ELL format is also going to work quite well because these matrices, because they're diagonal, right? That's not a very straight line. Then you're going to get the same number of non-zeros, more or less, per row. Okay, so the ELL format is also going to work well. Okay, so these other formats are not going to work so well. Right. And in fact, I just want to say one thing, which is that, so here, these red things are the CSR scalar format, right? And the green one is the CSR vector format, okay? So you can see that the CSR scalar format is going to work more and more poorly as you increase these the size of these matrices, okay? And basically what's happening is remember that one of the problems with the CSR scalar format was that, let's see if we can find this, was that you had this non-memory coalescing, right? Because you have to jump around to access different rows, okay? So as these Laplacian matrices get larger, the distance between the rows also increases, okay? And the bigger the distance, the worse your memory coalescing, okay? So that's why as the matrices get bigger, you get less and less performance. Now for the CSR vector kernel, right? Here what you want to do is you're assigning a warp per row. Okay, so therefore, if your rows are very small, right, then you're not using a large chunk of your warp. Okay, so this CSR vector is bad for like very small rows. So therefore, as you increase these the size of these Laplacian matrices, you're going to have more and more elements per row, right? So therefore, you get less and less waste per warp, and this is why you get better performance. Okay, and then you can see that this COO format, it's basically got kind of like a flat performance. It sort of doesn't care, how big the matrix is. Okay, right. So that's for the structured matrices. For the unstructured matrices, all right, for the unstructured matrices, let's see, what do we have here? Okay, so yeah, so one observation is that, well, the scalar kernel sucks, okay, right? So this is the poorest kernel, right? The COO format, basically, it's sort of, it doesn't care where the non-zeros are, okay? It's got very consistent performance regardless of which matrix you're working with. Okay, so all of these things down here, the protein, FEM spheres, and so on, they're names of different sparse matrices. Okay, you can actually go sort of download all of these sparse matrices. If you search for something like sparse matrix collection, you're going to get a website which has thousands and thousands of these sparse matrices. Right, so you can see what these guys look like. But sort of regardless of the structure of the matrix, you have that the COO format, right? Which is sort of agnostic to the structure, it performs more or less the same. Okay, all right. You get much better performance. So the CSR vector kernel, right? This is going to be much better than the CSR scalar kernel, Okay, but the best performance is actually the hybrid one. Okay, so the hybrid was a combination of ELL, right, and COO. Okay, so you get the best performance for hybrid. Okay, and the final thing to say is that so this GPU has a cache. Okay, now the cache is on the GPU is different from the cache on a CPU. Okay, so one thing is that the cache on a GPU is like really small. Okay, it's like 1 megabyte or maybe 1.5 megabytes. Okay, compared to like 12 gigabytes of main memory storage, and also the cache is actually implemented in the main memory of the GPU. Okay, so it's using physically the same hardware as the global memory, and it's located equally far away from the processing cores, and so therefore the cache on the GPU will not actually lower your latency, right? Because we know that the global memory has very high latency. It's got like 800 cycles latency, okay? And the cache is located at the same location as the global memory, so it's not gonna decrease your latency, okay? However, the cache, it basically allows that if many threads are accessing the same memory location, right? Then the cache will allow you to do like a broadcast operation to do all of these threads that are accessing the same memory location. Okay, so it'll help with your memory bandwidth because instead of doing these individual sends of the same value to all these threads, you're doing a broadcast, right? And so you can save some memory bandwidth. And so what these two final charts show on the right is that if you compare it using no cache, right, versus having a cache, right, and then here we're looking at the memory bandwidth. Okay, so previously we were looking at the number of computations that we could do for the SpMV, right? But on the right, we're looking at how much memory bandwidth we can achieve in SpMV, and you see that the cache is actually going to help. Okay. However, what's interesting is that the memory bandwidth only improves. So if you compare these two charts, the top one and the bottom one, right, you see that for the COO and the CSR format, right, there's basically no difference in the memory bandwidth, right? If you look at the blue dots and the red dots, right, on top and on the bottom, they're basically the same. Okay. The thing that does improve is the hybrid one, right? So that goes from basically like about 100 gigabytes per second to like something like 140, okay, or yeah. And then the CSR scalar also improves, right? It goes from like something like 80, 85 over here, something to like 110 over here. Okay. So I'm actually not sure why this is, but it's just kind of interesting that for most of these kernels, right, you don't get the improvement. Okay. However, for the hybrid format, you definitely get an improvement. Not on every single matrix, right? Because for example, over here for the hybrid format, okay, you're still not getting much of an improvement. Okay, but there are matrices where you get a substantial improvement, like what? Like this FM ship one, right? You're going from like something like 90 to 120 something. Okay, so that's all I have to say about SpMV. And then so next time we're going to look at another application for GPUs, which is breadth first search.